Okay, great. So, since we missed so many classes, let me just summarize what we've been doing in the last few classes, and then we can take it from there. Okay. So we are into this section of supervised learning, where we are doing something called as a regression. Uh, Within supervised learning basically means that we have from the data that we have, the data has a target class or a target label based on which we are trying to train a machine learning algorithm to behave uh, as close as possible to the input and output relation between the data. And within that approach, we have already seen classification. So we have seen multiple algorithms in classification, including KNN, naive-Bayes, decision trees, random forests, and we have tried some examples on classification as well. Then we move towards regression, and within the regression category, we looked at a particular algorithm called as linear regression. Linear regression is basically an algorithm in which the hypothesis looks like y is equal to theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x3 and so on till theta d xd if there are d dimensions in the data. So by dimensions, I mean d features in the data. Uh, and we have a cost function which tries to reduce the mean squared error. Okay, and depending upon if we want regularization or not, there will be a regularization term. Now, we saw that the main aim within linear regression is to be able to come up with the right weights or right parameters for the values of theta 0, theta 1, theta 2, so that we have a good relation between the input values, that is x1, x2, x3 till xt, and the output value, which is y. Okay. We saw that to update these values of theta, we can use an algorithm called as gradient descent, which basically says that uh, the new value of theta is equal to the old value of theta minus alpha times the gradient of the cost function. The gradient of the cost function will always be directed in a way where it will try to jump to a new point of thetas so that the cost will become lesser. Okay. And if we keep doing that for a long period of time, over multiple iterations, we will ultimately reach a value of theta where the cost is no longer reducing. And we would say that that is our optimum value. That is the value of theta that we want to settle at. Okay. To help us do this, we have the learning rate, which is also generally named as alpha. And by controlling alpha, we can control how fast or how slow we are moving towards our target. So a large value of alpha will allow us to go faster. A low value of alpha will allow us to go slower. The problem with going very fast is there is a very good chance that we may overshoot uh, our set point, and then we may actually diverge. So instead of getting closer to our solution, we'll be actually moving away from our solution. Okay. So using alpha, we can control that. We also saw how to implement this entire idea in code. So we implemented linear regression from scratch, that is implementing the hypothesis, implementing the cost function, the gradient descent, and we did it using vectorization, which was a fast way of doing things. So the same gradient descent, if we write it in terms of linear algebra, we'll end up with vectorized codes, which are much faster than your normal for loops and depending on that. Once we saw how linear regression can be implemented, we then said, let us also try it for a real case. That is, try it for an example which is a bit more extensive than the sample problem. And within that part, we started exploring this data set on Kaggle called as house price predictions. And then I think in the last class, we had done some parts of feature engineering of the house price predictions. So today's agenda is to go a little bit ahead and see if we can, I guess, finish this example and then move ahead to the next one. Okay. So within all of these parts, do you have any questions before we start? Okay, great. So in that case, let me go ahead. So what you're seeing on my screen is actually a Kaggle environment, and this notebook is generated here itself. As I said, this notebook is publicly available, so you can anytime log in and have access to this. Let me go ahead. So we start with importing our packages. So I'll quickly go through this because we have already done, and I think I remember where we had stopped last time, so we can start from there. I take the description data and print the file. The description data is basically for categorical information. It gives us the value of the category and some description on what that represents. And for numerical feature, it just tells us what numerical feature we are looking at and its value. We go ahead and load the data in df train df test. We look at its head, df train head and test head. So there are 81 features with I think 1459 data points, 1416 data points. And for the test set, there are 80 columns with 1459 test points. Here, the only difference is we don't have sale price. In the first case, we have sale price. So using all of this data, we are trying to figure out what the sale price should be. So for data exploration, I started asking certain questions and seeing how we can answer them. First question was, what are the features present? How many numerical and how many categorical? So I looked at the comment, I looked at the columns, I looked at the info. Then based on the info that we have here, I found that all the objects were basically categorical data. So I selected all the data types with objects and converted that into a list and put that into a variable called as cat features. Apart from that, there were additional three columns, MS subclass, overall quality, and overall condition, which were also categorical, but they were having numbers. So I added them also into the categorical list. For numbers, I took from the total set, subtracted the categorical features, subtracted the ID and sale price, and then we have our numerical features. So these are a list of numerical features, list of categorical features, 33 and 46, giving us a total plus 2, giving us a total of 81 columns. How many data points in train and test? We can find that by directly taking the shape. So yes, DF train has 1460 points with 81 columns. And DF test has 1459 rows or points with 80 columns. Are there any missing values? So yes, there are many missing values. So we print the missing values for the train set, and we also print the missing values for test set. So as soon as we see missing values, we say, okay, the next logical step would be, let us deal with the missing values, remove the missing values. So to deal with missing values, we have three strategies. If there are too many missing values, it makes sense to delete the column altogether. And if not, we will explore the data. Based on the data, find if there is a correlation between the multiple features. And if there is a correlation, can we use that information to fill the missing values? And finally, the third case where we don't have any option. In that case, uh, we will fill the missing values with the most common value for categorical and the mean value uh, for numerical. Okay. So in this case, we saw okay, pool QC is missing. Let us find out what is the data along with it. So if we check pool QC, we find that these were the options. So NA was not used. And when we checked the pool area, we saw many areas were zero, and those were the areas where pool QC was not involved. So we said, okay, let me simply add NA to these guys, and we were done with pool quality. Similarly, many of the features were this way. The categorical features were not using NA, which was a valid category as per the description. So wherever we found missing, mostly that was the reason. So we replaced all of these guys with NA. Okay, fireplace. Let's go ahead. Okay, this is where we ended our previous discussion, where we were working on lot frontage. So we saw that many of the lot frontage values were missing. So within the train set, we had some 259 values missing. And within the test set, we had 227 values missing. And we said, let us look at the different features associated with lot frontage. So along with lot frontage, we have lot area, lot config, and lot shape. And we said, let us do a scatter plot on lot frontage. versus lot area. So on the x-axis we have lot area, on the y-axis we have lot frontage. We saw that there are some outliers, so we have to deal with the outliers before trying to fill the missing values. So we said, okay, basically we put an upper bound on lot area and an upper bound on lot frontage. And after that we have this plot, that is the link again between lot area and lot frontage. And we said, let us do a regression plot. That is, let us draw a line that links both these values. And that's it. So now we're going to start a way of trying to fill this data. And what I suggested we do earlier was to use lot area as the feature and lot frontage as the output, and build a linear regression model between the two. It is ironic that in the big area of trying to show a regression problem for house price detection, we are also using linear regression in the smaller way to fill out missing values. Okay. So my approach was just take lot area and fill out, uh, create a model between lot area and lot frontage. But as Anand discussed last time, that we could also not only use lot area, but use the other features as well. So if we use maybe the features lot config and lot shape as well, we may probably have a better model that can give us the relation between these guys and lot frontage. And we agreed, yes, that was a fair enough idea. And then we said, okay, let us write code for doing something like that. So in this case, our train data will be all the data points for which we have information, for which we have lot frontage. Okay. If we have the link between lot area, lot shape, and what's that, lot size. If we have the link between these guys, then we will use that as training data. And every other case where we don't have the relation between lot frontage and other ones, we will use that as test data, or test data or unknown data for which we'll predict the information. So from the known values, we learn a model and then predict it for the unknown values, and thereby we will have a missing value split. Okay. So we said, okay, let us load from scikit-learn's linear model. Let us load a function. Let us load the class linear regression, and we divide this into two parts. If lot frontage is null, and that is equal to false, that means it is not null. We store that into locations of lot underscore not null, which will be our training data. And when we see that, okay, when we see that we have lot frontage is null is equal to true, that is our missing information, and that will become our prediction data. So we divide this into two sets. The first part, we will create XMIS, which is the data for training the model. So I could even call it xtrain, but I did not take it xtrain because later on we'll be using xtrain. So we call X missing values, the X for missing values, that is the features for missing values. That will be lot area, lot config, lot shape. We take that into XMIS, then we check the head. We see that, okay, this will be our input data to the model. Then since lot config and lot shape are actually categorical features, we said that let us do get dummies on them. So first, since these are numbers, since these are strings, we cannot feed it to the regression model. We'll have to convert this data into numbers so that we can feed with the regression model. That is first point. Second point is these numbers are actually, these categories are not actually linked to each other using they're not linked to each other using ordinal data. That is, inside is not greater than FR2, or inside is not greater than corner, and so on. So since there is no numerical relation or ordinal relation between these guys, it makes sense to convert them into one-hot encoding. So we use pd.getDummies. Okay, we use pd.getDummies over the columns lot config and lot shape with the prefix lc and ls, so that we can convert these guys into corresponding columns. So once we apply that, let us see after the application of get dummies, how does this code look? So if we do a head over this, we can see that now we have a lot many columns. So wherever we had lot config, so instead of lot config, we have LC corner, LC cul-de-sac, LC FR2, LC FR3, LC inside. Basically the different options that were present within lot config. Now we have those many columns, and depending upon the case, one of these values will be one, depending on what we want to store. So we have converted that into one hot encoding. Additionally, we have converted that into numbers that can be fed to the model. Similarly, looking at lot shape has also come into LS IR1, IR2, IR3, and LS REG, which are the different options that are available for lot shape. So that becomes our training data. From DF train, lot frontage is the value that we are trying to predict. That will be a target in our case. So we will take all the not null values, that is all the training values that we have for XMIS. We can see that there are 1201 points, and similarly for head also, for XMIS also, we can probably check how many points are there. Let me see XMIS dot shape. And we can see that again here also we have 1201 points. So the numbers match. We've got 1201 data points, for which 1201 data points, 10 columns, and one feature that we want to put. Okay. So with this, here, okay. So now I am doing it for all the values as well. So I think the purpose behind this is so that we will now be able to extract from this the DF test data, okay, or the unknown data for this. So maybe I can explain this later on. Let us go down first. So we take the linear regression model, create an instance of the linear regression model into the variable LRMIS, fit the linear regression model using XMIS and YMIS, which is the training data for our for the training data that we will be using to create a model. So XMIS, YMIS. Once we have XMIS and YMIS, we are doing, let's predict this answer for all the values. Okay, so we'll predict, we'll predict it for all the data points. What will be lot frontage prediction? So for all the, after training with the known values, we predict for all the values. Once we have predicted for all the values for lot, area, config, and shape, we now see that we have to replace only the ones with missing values, right? So in this case, we will use the np.where function. The advantage of using np.where function is it takes three inputs. The first input is a Boolean set of rows and columns, a Boolean set of multiple list values or rows here. And then depending on what is the value here, whether we have a true or false, the first or the second input will be passed. Okay? So if we have a true, the first input will be passed to the output. And if we have a false, the second input will be passed to the output. In this case, what we'll do is we are taking the entire column of DF train lot frontage, and if is null is equal to true, then the data is actually missing. And if the data is missing, we will load it from lot frontage prediction, that is the prediction from our regression model here. Okay. And if the data is not missing, then we will use the original value, and the original value actually has the data. Okay. So executing this, now we would have populated lot frontage with all the values. So we do the same for our test data. So again, it's just a repetitive process. The same idea that we did for train. We are taking XOL test, we are getting dummies. Now we don't need to train a model. Okay. The model that we trained for the train data should be enough to predict for the test data as well. So we just use the same model, predict it for test, use the same criteria, populate lot frontage, and then we delete the two extra columns that we created, the lot frontage underscore pred functions. Okay. So once we do all of that, now when we look at the missing values, we can see that, okay, we have dealt with lot frontage. That is, we don't have any missing values for lot frontage. Okay. So uh, this is this is probably a fairly advanced step to talk about in your initial pieces of code. This just goes to say that we can do a lot of things. Okay, there is no set way of doing things, and depending upon what the situation is, we could apply either simple rules or either complicated rules. So had this been probably in the early days of my data science journey, I would have simply taken lot frontage and replaced it with the mean values. Okay, and I would have stopped there. But with some experience now, I think that maybe we can do something more smarter. So this was actually a smart thing to do. That is, use the other features that may be linked with lot frontage. So lot area, lot config, lot shape, and can we develop a better model that will be help that can help us to fill the missing values. Okay. So we went through this exercise of doing all of this drama. Okay. Do you have any questions before going ahead? Okay, great. So in that case, let me jump ahead. So we'll look at other features. So the next feature to look at is garage. So we do a quick search and we see that all the missing values for garage, all the 81 missing values for garage here, uh, as we got in the test, all the 81 values are basically the data where garage area is 0 and garage cars is 0. Basically that there is no garage, that is why uh, all these features are missing values. So we said, okay, the job is simple. We'll replace it with NA and we'll replace the garage year built with 0. Now, when we look at our data, we have dealt with garage. Let's go to the next value, basement. Again, same idea. We see that all the values with missing values are actually data where we don't have a basement. Okay. So if that is the scenario, we'll replace with NAs and we've dealt with missing values. Then we've got Mason veneer type, and we say let us look at Mason veneer type and area. Both are not defined, so we replace all missing areas with 0 and all missing veneer types with NA. We have one data point, only one data point missing for train, but we have multiple data points for test, so we'll have to handle them again. So for train, we replace with the most common answer. So for train electrical data, we replace with the most common answer, which is, I think, S breaker, some breaker of some type. So we replace that value. Now we see that, okay, train has no missing values. Test has some missing values. So we go ahead, see what missing values. So MS zoning, functional, all these simple things. So we see MS zoning, we find the most common is RL, we replace by RL. Functional, the most common is type, we replace by type. Value count of utilities shows all pop, so we replace by that. And basement, full bath, and these all quantities, we will just explore, replace with their modes, and take the square feet areas and replace with zeros. Then we have cell type, garage cars, and so on. We replace those values with the mode as well. And finally, after a lot of time, we have dealt with all the missing values. And now we can actually move towards our regression. So let's go ahead. Now that we have processed data, that means we have data where there is no missing values. Let's see what other steps are required. So for all, if you remember in the beginning of the phase, we divided our features into categorical and numerical. And the main purpose behind that, along with, of course, along with missing values, the main purpose was to decide these two kinds of steps. That is, if we are in categorical, we can do something called as one-hot encoding with our data. And if we are in numerical, then we could try to normalize our features or scale our features and do things like that. And if you remember in the last class or in the last few examples of classification data, we explored something called as pipelines. And we saw how pipelines can be very useful in getting us reproducible results, or in getting us ways of doing things in a more systematic order. So here, that is the first step we are doing, data modeling. That is, now we are trying to prepare the data for using our machine learning algorithms. So within that process, from scikit-learn.base, I called base estimator transformer mixin. This will be the base classes that we will use for creating our custom class. Then we call two pipeline methods, pipeline function and feature engine, and they will help us to create the pipeline for categorical, numerical, and so on. And we're calling within from pre-processing, we are calling two classes, standard scaler and one-hot encoder. We'll use standard scaler for numerical data, and we'll use one-hot encoder for our categorical data. So with that in mind, we create our first class. So let me run this. We create our first class called as data frame selector. Here, the only task that this class is doing is, before running the pipeline, you would have to choose on what features the pipeline will run on. Okay? And the data frame selector is the Pythonic way of doing that. And additionally, since our pipeline is made from scikit-learn, scikit-learn expects that the classes that we will call will have 2 or 3 different kinds of functions, specifically the fit function, the transform function, and the fit transform function. So we, just to meet scikit-learn's criteria, we write this class with 3 attributes, 3 functions, 3 methods. The first is the init method, just simply takes the attribute names. The second is the fit method, that basically does nothing. And then the transform method, which just selects the attribute names that we started off with and gives the values to the next level at the pipeline. So we call this function. We take our entire DF train and divide that into X train and Y train, for the simple reason that X train and Y train are standard terms, especially in terms of machine learning. X is the features that we want to train the model for. Y is the target that we want to learn. So we do that. We look at their shape. We see that we have 1460 rows with 79 columns, which is expected because we started off with 81 columns. The 2 columns were ID and sale price. So we have removed ID and sale price from X train. We have actually converted sale price into Y train. That will be a target level. Okay. We create the first pipeline, which is the numeric pipeline. And within the numeric pipeline, we are having 2 steps. Okay. Step 1 is we will be selecting all the numerical features. So we are doing that using our data frame selector that we created here. And we are just passing the list of numerical features to this. That is step 1. And after selecting our numerical features, we are simply scaling those features down. So that is a numerical pipeline. If you remember, when we say scaling, scaling is basically standard scaler will do something called as standardization. And it will transform your X into X minus mean of all the different features divided by the sigma of the features. Okay? So that gives us that transformation. And once we do that, once we have created our numerical pipeline, let me execute this. We can then do a fit transform with the X train. So our X train, you see here, had 79 columns, but here it will extract only the numerical values. So if I am correct from earlier, we have, so let me not go so far. We can directly print the numerical values here itself. So if we do a num feeds and dot shape, probably it will show us. Okay, no, we'll have to do length of num feeds. And we can see that there are 33 numerical features. Okay, we started X train with 79 features, but since we are selecting numerical features alone, we expect that the output of this fit transform should have only 33 features. Okay, so when we execute that, we get this output, and let us look at the shape of this output. So as rightly expected, we have the same number of data points as earlier, but we have only 33 columns. And these 33 columns are basically the numerical features. And if you look at the values, these numerical features have been standardized so that all of the values, all of the columns will have a mean of 0 and they will have a standard deviation of 1. So this will put everything in similar ranges so that our algorithm will not get confused while training the model. Okay? It will not assign unusually high or low biases depending just because the range is big or small. Now we have dealt with the range. Okay? So let me delete this. Go ahead. So that is our numerical features. Next, we will try to do that deal with the categorical features. So if I okay. So here in categorical features, first step, we will select the categorical features. Step 2, we will call one-hot encoding. And what one-hot encoding will do is for each of the categorical features, it will convert them into one-hot, it will do get dummies over them. Basically, for each unique categorical value, we will have an individual column, which is a Boolean value, which either says 0 or 1, depending on whether the data was matching that particular column within the original categorical features. Okay? So we execute the cat pipeline. We see that here we had 46 features for cat features. Okay? And when we call the pipeline here, we can see that now we end up with many more features. We end up with 301 features. Okay. So here it is very difficult to verify if this is right or not. Basically what we will have to do is we will have to see each of the 46 categorical features, count the unique values within them, and then add all of these values. And that will be the number of rows that we will have for our categorical pipeline. Okay. So let's just hope that we were right, and we have 301 features that represent categorical values. But we don't want our two pipelines to be separate. We want to create one full pipeline that can deal with both the numerical and categorical features. So we can easily do that by calling the function feature union, which will take the list of pipelines and attach it into parallel pieces of code and then put it up for us as full pipeline. So we take the numerical pipeline, categorical pipeline, and create something called as full pipeline, which we can directly do a fit transform on. And we see that now we have 334 features, which is 301 features for categorical and 33 features for numerical. Adding both of them, we have 334 features. So this one line, it takes all the numerical features, does standardization over it, takes all the categorical features, does one hot encoding over it, and returns for us the final result. Okay. So since we have this, now we copy this into a variable called as x prep train, that is x preprocessed train. So that does the first part of our code, that is preparing data for modeling. Now we can go ahead and try some models. Okay. Before going ahead, do you have any questions? Have you understood how these pipelines are working and what is the purpose behind them? Okay, great. Let me then go ahead. Once we have our pre-processed data, we will try some models. So within our regression category, we have three models that we'll try. We'll try linear regression, we'll try ridge, and we'll try lasso. Okay. So linear regression is something that we've been seeing so far. Ridge and lasso are two algorithms in which we have added the regularization term. Okay. I don't remember since it's been so long. Do you remember, have we talked about regularization within our slides? Oh, we have not talked about it. Okay. Okay. So nonetheless, let me go ahead and use them. And then later probably I'll talk about how these work. Okay. In short, what we are doing is ridge and lasso have the same cost function as the linear regression, but additional to the cost function, there is one more term that takes the sums of all the weights together, multiplies it with a value called as lambda, and adds all of these values into the cost function for linear regression. Okay, so when we do that, what we are also ensuring is we are ensuring that in the process of linear regression, our values, our weights will not be very high. Okay, our weights will actually be will try to be the minimum so as to get the lowest cost. And the advantage for that is that we will prevent something called as overfitting within our body. Okay, so that is the basic purpose of doing that. Nonetheless, we can use ridge and lasso even without understanding those concepts, because as we saw, most of these ideas are black box, and we can try with multiple options and still get for us a good enough result. Okay, maybe after we finish this, I will try to explain what regularization is. So we call the three linear models: linear regression, ridge, and lasso. From sklearn, scikit-learn's model selection, we also call cross-validation score that will help us to do cross-validation. Then we call k-fold that will help us to do, again, it will help us in cross-validation by splitting the data into multiple folds. And for the error, we will check MSE. MSE is mean squared error. In fact, we'll be using MSE to get a root mean squared error, RMSE. Okay, let's go ahead. We load all these required packages. We define k-fold, which will be a k-fold cross-validation with 5 splits. We start with our first model. Our first model is linear regression. We take its copy, we create an instance of linear regression into LR underscore reg. Okay. Then we do a dot fit with the prepared or pre-processed data and Y-train. So that will simply fit our model with all of the data. And we will do a predict over all of the trained data. And we will check how close our Y prediction and our Y train is. So this is just training accuracy. We are training the model with all of the data, X train and Y train, and predicting what will be the value of the output when X is the input and Y prediction is our prediction. Once we have this prediction, we can compare between Y train and prediction to see how good we are doing. So we are not doing validation at this point. We're just trying out linear regression to see how good it works. And we see that our mean squared error comes to be as roughly very close to $20,000. Okay. So what this basically means is, on an average, we are wrong up to $20,000. Okay. For the different house prices, we may be wrong to that level. Okay. Let us now do a cross validation on this and see if we are getting an average out. Was this answer of just the train accuracy and an overestimation or not? So when we do cross validation and we check for each of the folds, we see that these are the different points, these are different scores that we are getting, and our mean on an average, we are wrong by $35,000, not $20,000. We are wrong by $35,000 with a standard deviation of around $8,500. So this is this difference between just our training score and our validation score shows to us that there is a problem of overfitting. Okay, there is a problem of overfitting. How do I know that? Because my training accuracy or my training MSE, RMSE is very different than my validating RMSE. Okay. So I clearly have an overfitting problem which we need to resolve. Okay. So again, overfitting can easily be resolved using regularization, which I will explain later on. So now, since we saw that, okay, we can train them, at least the base run works fine. The model is not throwing any errors. So we can go ahead and try to make this better. Okay. To make this better, we will call the grid search method from sklearn's model selection. And again, we used grid search within our classification examples also. And the purpose of the grid search is basically to try out different hyperparameters of our machine learning algorithms and to see which one works best. Okay. So if we do it manually, it will take a lot of time. But if we have an automated code for doing this, then probably we can save a lot of time. We can be more systematic, and we can get our answers faster. Okay. So here we start with linear regression. This is the same piece of code or very similar piece of code that we used for classification. And I will just change the relevant values from classification to regression. So first case, when we start linear regression, we don't have any parameters actually. Linear regression is a very simple model and we don't need to modify any parameters. Nonetheless, I keep this here. Okay. Nonetheless, I keep this here so that I want to use this for ridge and lasso as well. So we start with our parameter grid. Let's assume that there are many parameters that we want to try. We take a copy of linear regression into LR, right? Now we create a copy of grid search, which takes this estimator, this parameter grid, the k-fold that we described earlier with 5 values. It tells us what will be our scoring. So we will check if our model is doing good or not based on this metric. The metric is negative root mean squared error. Okay. So it is basically RMSE, root mean squared error itself. The negative here just allows grid search to, to maximize the evaluation matrix. Okay. To just find that. Otherwise, if we take error, the idea would be to minimize the error and not maximize the score. So just so that everything is uniform, we will change the metric to negative of mean squared error. Okay, and when we do that, when we change the metric to negative of mean squared error, we know for sure that that grid search it just has to maximize this value. Okay, so I keep verbose as one so that we can see some hints when it is running. That will be a copy of grid search. Then we will fit the model just like any scikit-learn thing. Scikit-learn model will take grid search.fit with our pre-processed data or prepared data along with bytrain. Once we do that, we can print the best parameters. In this case, it does not make any sense because there are no parameters. Nonetheless, we can print the best parameters, take the best estimator, put that into LR, right? And then do a cross validation for this best estimator. After doing cross validation, we'll take all the scores, the mean scores and standard deviation and store them for this part where we'll be adding all of this into a pandas data frame so that we can compare between multiple algorithms. Once we have trained the model, once we have done cross validation, now we train the model again with all of the data so that we are using all of it. Once we have a trained model, we'll try to predict for our unknown cases, unseen cases. Once we have predicted, we will find root mean square error, and this will again help us to populate this data frame. So I execute this part, and here since it's only 5 folds, I think it finished in just 2.7 seconds. And within 2.7 seconds, we saw the same thing that we had expected by running linear regression alone. That is, we are getting a train RMSE of around $20,000. We have a validation RMSE, root mean square error, of around $35,000 with a standard deviation for validation as 8,500. So this is not a very good model. Let us move to the next model and see. So our next model is rich. You see, everything else remains the same except for this one part where we are now telling Ridge that you should try all of these parameters. So alpha within scikit-learn's definition is the same lambda that I will be talking about, and it helps us to control what is the level of regularization we want. Lower values means less regularization. Higher value means more regularization. Okay, so our model will move from high variance to high bias. Okay, as we keep on changing alpha from lower value to higher values. Everything else is same. Instead of regression, we have put ridge. And now once we execute this, let me run this. Okay, so once we execute this, it says that we have 5 folds with 50 fits, and just in 2.4 seconds it was able to run through all 50 options. And after running through all 50 options, now we can see our train RMSE and our validation RMSE. We can see that our train RMSE earlier was very optimistic. Now we are becoming a bit more realistic in nature. So we moved from $20,000 as our error to now $25,000. And we saw that our validation RMSE, instead of 35,000, it has reduced to 31,000, which is good. Okay, we are basically means that we are improving. And for this case, it chose an alpha of 15. So it said that an alpha of 15 actually helps it so that we can become better with our score. Let's try this for lasso. So within lasso, there are three parameters that we want to try. One is tolerance, max iteration, and alpha. So I ran this earlier, and it actually takes lasso a huge amount of time to execute. So I limited the iterations to only 2000 iterations for every sample. And apart from that, everything else is same. When I execute this, you can see that it takes 50 examples. Let's see how long it takes to run. Okay, so this finished in around 9.5 seconds, and we saw that lasso also is not actually very good. It gave us the results very close to linear regression for train RMSE, and for validation RMSE, it became a bit better. Nonetheless, our choice would go with Ridge. So now, finally, since we have shortlisted our algorithm and we have found the best, we have fine-tuned this algorithm Ridge as well. Now we can go ahead and we can train the final model and predict it for the actual test data and then upload it on Kaggle. Okay. So when we do that, we can see from DF test, we will take the categorical features and numerical features into X test, create the pipeline, use the same pipeline as before to prepare the data. Then we use lasso. Okay, we should in fact use ridge. So let me take a ridge regression. Where is that? Okay, ridge regression as our model. So we'll use that ridge regression. So this trained model, we will just use it to predict it for our test data. Once we use that model, we can see that this is how our prediction looks like, which at this point we have no ways of identifying what is right or wrong, because Kaggle for the test data, it has not given to us the actual answers, and we will only have to upload it to Kaggle, verify its score, and that is the only way to know how close or how far we are. We get the prediction, we attach it into okay, let me change that to Ridge. We store the result into a CSV file, and this is the head of the CSV file. Okay, this is what our prediction looks like. Now that we have our predictions, we can actually upload it on Kaggle. Before going ahead, do you have any questions in this part of uh, fine tuning and then further testing and deployment? Okay, great. So the process is actually very simple. We used similar ideas that we used for classification algorithms, and then we are just applying it for our regression case. Okay. Now that we have our model, let me. So within Kaggle, I will have to first share this and keep it public and just click on save. It will take some time. Oh no, this I've already done. I have to do a save version here. So I have to do a save version for save and run all. So this will be version 3 of my file. I will execute this. It just takes a few, maybe a minute to run all values and to save the output file of here as well. Then we can move back to our Kaggle environment and then upload or submit this file for evaluation, and then we can see what score we got. Let's wait for a few more minutes. Okay, so once this is completed, now we can move on to, we can leave the editor, go back to Kaggle. Now if I go to the competition on on house price predictions, I go to notebooks, your work, and here I think now you can click on, let's come to public. No. Okay, we can come to submission, click on my submission, and this was the previous version. Now, okay, I've forgotten how to submit for, let me try this. If I do submit predictions, it will say to upload the data. No, if I go to notebooks, and here, okay, yes. After saving, we have to open the notebook outside the editor. Go to the section of output. So now we have the output. I had saved that into ridge sub.csv. Now from here I can submit the data. So when I submit it, I want to submit it as notebook version 4 ridge sub. All that is fine to this competition. That is fine. Let me submit. This is your entry has been submitted. It could take a while before your submission is scored. Generally, it takes very less time. So let me go to view my submissions, and we can see that with with ridge, this is our score. That is earlier it was 0.5872. Now it is 0.5023. So basically, our score has reduced down. Okay. So probably because of some of the decisions. I think the decisions associated with maybe the decision associated with filling the lot frontage and so on. Because of that, our score became down. The agenda would mean that now we would want to improve our score. In fact, on the leaderboard, you can see many people have excellent scores uh, of the order of 0.00044. That is much less error. Uh, and we are somewhere at this point. Okay, so we are somewhere at this point. Oh no, sorry. A lower value of the score says that we are doing better. Okay, a lower value of the score says we are doing better. So we have improved a little bit. We can do better, of course. We are only at 3,000 points, 3,000 rank. So I think few things that we can work on that can make this model better is something called as feature selection. So instead of having all the features, we can either pass some set of selected features which can give our answer, which can become a better answer to our model. So either that, do it manually, or we could use something called as PCA, which is principal component analysis, which will help us to uh, choose some elements, some key features automatically that is actually a mixture of multiple features, so that our model will become simpler. Simpler models are generally less prone to overfitting. So that could probably be the next step. Maybe you guys can take my notebook ahead, fork it, and try to make those changes, and let me know if the score improves or not. Okay. I think we can stop here for today. Do you have any questions apart from this? Okay. Okay. Great. So Sure. Let's stop. Let's meet again day after tomorrow. Uh, if you have any questions, of course, you can post it on the WhatsApp group, and then I'll try to answer. I would strongly suggest, keep on practicing. Uh, at least try one data set per week, so that you don't lose touch of all the things you have learned so far. So the key thing within data science is the concepts are not hard, the programming is not hard, but there are many concepts, and there are many tips and tricks to remember. Okay, so the problem with such things are, if you don't practice them enough, you will have a very high tendency of forgetting what they mean, and over a period of time, then you would have lost everything. So it is very good to keep on practicing as much as possible. So with those last words, let me stop sharing, and I'll stop recording as well.